So for the average value of x, we're going to do it for the n equals 1 state. You're going to do the more general case for any n. What we need to do is take the integral from x equals negative infinity to x equals positive infinity, integrating over x, wave function star 1 of x and t, put my operator, which is just the function x, then put the wave function itself of x and t. Now, we already know that the wave function is 0 for all positions outside the box. So the integrand is 0 for those ranges of x. So that means our contribution to the integral will only happen between the left and right ends of the box, which goes from 0 to L. Then for my wave function, I have a constant b times sine of pi over L times x. I should be taking that as its complex conjugate. The sine function is a real function, so its complex conjugate is the same as sine pi x over L. B in principle could be a complex number, so I'll put a star there. Then I have to put my x, and then I have to put the wave function again, but not conjugated. B sine pi over Lx. Alright, so I need to do that integral. B is a constant, and b times b star is just magnitude of b squared. Integral from 0 to L dx. This is now sine squared of pi over Lx times x. So the easiest way to do an integral that has sine squared in there is usually to use a trig identity. So we know from trig functions that for any theta, sine squared of theta is always 1/2 of 1 minus cosine of 2 theta. And so I'm going to use that where theta is going to be pi over L times x. So average value of x for n equals 1 is going to be b squared integral from 0 to L dx 1/2 1 minus cosine 2 pi x over L. And then I have my x operator. So now I've reduced my integral to this. I'm going to distribute x through both of those terms. B squared is still out in front. So now I'm going to get the integral from 0 to L dx of 1/2 x minus integral from 0 to L dx of 1/2 x times cosine 2 pi x over L. Alright? So I've multiplied my x, I've distributed it through there. Alright? Well, this integral is pretty easy. So I've got b squared integral of I'm going to pull out my 1/2. I've got integral of x dx. Well, that's 1/2 x squared. I have to evaluate that between the limits of integration of my definite integral. So that's going to give us that first integral. Then I have to do this one. So this is the integral. I'll pull out my 1/2 integral 0 to L dx. I've got to integrate x times cosine of 2 pi x over L. So that's going to be an integration by parts, which I'll show you on the next page. I'll just go ahead and I'm going to rewrite this x cosine 2 pi x over L. Do that integral in a minute. All right, this one is, there's my b squared, is 1/4 x squared evaluated at the upper limit of integration is just L squared, minus x squared at the lower limit of integration, well, that's just 0. So I've done that first integral. I still have to do my second one, cosine 2 pi x over L. Alright, so now we're going to take a look at this one that I've just underlined. That's going to be an integration by parts. I'm going to do the integral from 0 to L dx of x cosine 2 pi x over L. Let's call that integral I. So let's let u equal to x. dv is going to be cosine 2 pi x over L dx. du is just dx. And I have to do an antiderivative here to find what v is, but I know how to do an antiderivative of a cosine function. So v is going to be L over 2 pi sine 2 pi x over L. And I can check that by differentiating dv dx. Let's just check it. dv dx, if this is v, is L over 2 pi. Chain rule applied to this. The derivative of a sine is cosine of its argument. And then chain rule, I have to bring down the derivative of the argument with respect to x, which is 2 pi over L. And it looks good, because dv dx is just cosine of 2 pi x over L, which is what I was hoping for. Alright, so this is my v. So integrating by parts, I know that I is uv evaluated between my limits minus integral v du evaluated between my two limits of integration. So the function u is just x, and the function v is L over 2 pi sine of 2 pi x over L. I'm going to integrate that, evaluate that rather, between my two limits of integration. That's my first part of my integration by parts. Then I have to do minus integral from 0 to L du, well, du is just dx, times v. V is this function here. Alright, so this first part of my integration by parts I have to evaluate at x equal to L. So I sub in x is L in both places. I'm going to get sine of 2 pi L over L. Well, that's sine of 2 pi, which is 0. So my upper limit of integration evaluates to 0 for this term. Also, my lower limit of integration evaluates to 0 because I'm going to sub in 0 for x. In both places, that's 0. So this part of my integration by parts just goes away. So my integral really comes down to this last part here. And I'm going to copy that to the next page. The integral I'm looking for is negative integral from 0 to L dx L over 2 pi sine of 2 pi x over L. And that one I can do, an integral of a sine function. I'll bring out my constants, L over 2 pi. So now I have the antiderivative of sine of 2 pi x over L. Well, that is just negative cosine 2 pi x over L times L over 2 pi. And then I have to evaluate that between my limits of integration. So simplifying this, I've got a minus sign from my integration by parts. I've got another minus sign from my antiderivative here, so those go away, and I get L squared over 4 pi squared cosine of 2 pi x over L evaluated between those limits. If I sub in x equal to L, I'm going to get cosine of 2 pi for my upper limit of integration minus cosine of 0 when I sub in my lower limit of integration. Cosine of 0 is 1. Cosine of 2 pi is 1. 1 minus 1 is 0. So this integral is actually 0. So the integration by parts that we just did, I'll remind you where that came from. We were trying to find the average value of x for our n equals 1 state. And we did trig identity to break that into two integrals. We just showed that this second integral is 0. So our answer for the average value of x is really just what we got from the first integral. And so average value of x for the n equals 1 state is b squared times 1/4 L squared. And as you will show in another one of the homework problems, the coefficient b for any n is just square root 2 over L. So we're going to use that fact right now and go ahead and sub that in to find the average value of x is b squared is 2 over L. Then I have to multiply by 1/4 L squared. I just get L over 2 for the n equals 1 state. The average value of position, if I prepare many, many particles in this, identically prepared in this infinite box, and measure the position of each of those particles, I'll get a random number somewhere between 0 and L each time. But if I find the average of all those measurements, I'm just going to get L over 2, which I hope makes sense intuitively to you. And we'll talk more in class about why that answer makes sense.